again and again. It's not looking good. The atomic memory order acquire and release define how memory operation on different threads are allowed to be ordered around atomic operations. Acquire. This is used on atomic load operations or other acquire operations. An acquire load acts as one-way barrier. Memory order acquire, okay. One-way barrier. Oh my god. No reads or writes in the current thread can be reordered before this load. In other words, when you perform an atomic load with an acquire semantic, subsequent operation in the thread will not start until the load is completed. Additionally, all writes made in other threads on the same atomic variable that were tagged with the release semantics become visible to the current thread after the acquire load. In other words, when you perform atomic load with the acquired semantic, subsequent operation in the thread will not start until the load is completed. Additionally, all writes made in other threads on the same atomic variable that were tagged with release semantic become visible to the current thread after the acquire load. Ensure that once you acquire a value from another thread, you also acquire visibility of everything that other thread did before the release. Release. This is used on atomic store operations or other release operations. A release store acts as one-way barrier before the store. In release store, no reads or writes in the current thread can be recorded after the store. In practice, this means all the memory writes in the current thread are completed, flushed, before atomic store with release occurs. Furthermore, all writes in the current thread, even to the non-atomic variable, become visible to other threads and later perform acquire load on the same atomic variable. In short, when a thread releases a value, it publishes its prior changes to memory so that they can be observed by another thread that acquires that value. This semantics create half fence or one-way memory barrier. Acquires stop memory operation after the atomic load from moving before it, and releases stop memory operation before the atomic store from moving after it. Unlike the full two-way fence, acquire and release don't order everything in both directions. The only order relative to atomic operations, an acquire operation guarantee that any reads and writes after acquire cannot happen before it. Release operation guarantee that any reads and writes before the release cannot happen after it. This is very good line. Hi Elena, how are you? This is very good. Good, how are you? I'm okay, not too bad. Thank you so much. Blunt, yo, what's up, Blunt? How are you doing today? I subscribed and thank you so much. Thank you so much. It really means a lot to me. You guys are really good. Thank you so much. Role in thread synchronization, release, acquire, ordering. Okay, STD memory order, acquire. Acquire and release work together to synchronize memory between threads. Like. Thank you so much. Thank you so much. The typical pattern is that one thread performs a release store. Everyone subscribe and like. Thank you so much. You're shouting out for me. That's a really good thing. One sec, I'll be back. No problem, I'm here. Together to synchronize memory between threads. The typical pattern is that one thread performs a release store on atomic variable. The thread performs an acquire load from the same atomic variable. When the acquiring thread actually observes the value returned by the releasing thread, the synchronization between with the relationship is established between two operations. In effect, the release operation happened before the acquire operation. All writes in thread A before the release become visible. Well done. You hit 1000 subscribers and 400. 400. What 400? You mean 4000 watch hours? No, I haven't reached that point. I'm still at like 700 watch hours. $1400. Oh, okay, yeah. I've reached 1400, that's for sure. Subscribers, yes. I need 140k, come on. All writes in thread A before the release store become visible in thread B after acquire load that reads the value. The threads are synchronized. The acquire load will see memory in a state that includes everything done up to the release store in other thread. Formally, if an atomic store in thread A is done with the release semantic, an atomic load in B thread of the same variable is done with the acquired semantics, and load reads the value that was stored by A in A store synchronized with B's load. This guarantees a happens before relation everything that, for example, when you are older, I bet you gonna be like 100 million subscribers. Oh, really? Such nice words, you know. I don't know. I don't have any hopes. My job is to just stream every single day, and I'm doing that. So it's good. If I reach that number, it would be like awesome. I will go over, uh, I will just dance like anything. But I'm not expecting anything. Expectations are bad usually. If they are not fulfilled, I wish I could donate, but I'm broke. It's fine, no need to donate, it's fine. My my channel has no monetization on, so even even if you want to, I can't take the donations. Whew. Let's continue grinding. If an atomic store in thread A is done with the release semantics, and atomic load in thread B of the same variable is done the acquire semantics, the load reads the value stored by A. For example, mutual exclusion locks internally use release acquire semantics. Oh my goodness. This is a very good thing to be aware of. Oh. One day you're gonna be really good at YouTube. I really inspire you. Thank you so much. You're so good. You're so good. You are such a good soul. Thank you so much for saying good things and really inspiring me. I'll see. I will continue putting my efforts on YouTube, okay? Just because I have people like you on my channel. Thank you so much. When a thread releases a mutex, unlock it. It does so with release semantic when another thread locks the mutex. Sorry, I have to go. I will be back tomorrow or when I can because I have children. No problem. Thank you so much for joining. Take care of your children and do good. Hi. Hi, hi. It does so with acquire semantics. This ensures that all operations inside the critical section by thread A before releasing the lock are visible to thread B after it acquires the lock. Okay. Important, the synchronization only occurs if acquiring load actually observes the value stored by the release. If the load happens too early, before the store occurs, or before it writes the expected value, then it will not see the released value. No synchronization with it won't establish the synchronization. In other words, an acquire operation does not inherently wait for the release to happen. It simply guarantees ordering if the release is seen. The programmer must ensure the coordination by using a loop or other signaling to make the load actually read the release value. If an acquire load reads an old value that was not produced by the release store, then no synchronization occurs. Other memory writes may not be visible yet, potentially leading to a data race. Okay, so we have flag atomic. So we have include atomic, include thread, assert, IO stream. I don't know why they need assert, but okay. And then we have bull ready, flag indicating data readiness, shared data, non-atomic. Okay, so we have a producer thread, data 42, write to shared data. Okay, ready store, true, memory or release, release store, signal readiness. Atomic bull ready false. The flag is indicating data readiness. Okay, so there is an atomic variable. It's like a flag and it's currently false. Now, producer, we have data 42 ready store true. Store release store to signal readiness. Store true. Send a memory order release. Consumer. Okay, while ready load. Memory order acquire. Wait until the data is ready. Spin wait. Okay, and spinning until ready becomes true. Store load std memory order acquire. So consumer is taking acquire, it's taking the code, it's taking the load, and assert data is equal to 42 should never fire, data is visible. Okay, share data value. Okay, so thread. In this example, the producer writes non-atomic variable data that performs atomic store ready with release data. Okay, I understood. C++ offers, okay, multiple memory orders for atomic operations. Acquire, release, sit in the middle in terms of strength. It is useful to compare them to other common orders, relaxed and sequentially consistent. Memory order relaxed, this is the weakest ordering. A relaxed atomic, okay, let's try to gather as much as possible. Okay, why to not gather information, you know. Relaxed atomic operation provides only atomicity and no ordering guarantee at all. With respect to other memory operation, no acquire or release semantics are involved. This means relaxed load store does not establish synchronization. Threads may not see each other memory writes even if one writes to atomic and other reads. Hi, Lily Pop. Hi. Welcome. Relaxed is useful for things like counters or flags where you don't need ordering. Okay, no ordering. Since the writes data could be still hidden due to lack of synchronization, in short, Relax gives no guarantee about visibility of other writes. It only gives atomic operation itself. Okay. Okay, acquire release. Using memory order release on writer side and memory order acquired on reader side. Okay, often called release acquire pair, provides a happens before guarantee between threads as described above. It is weaker than full sequential consistency but much stronger than relaxed. Acquire release act as the minimum ordering needed for the safe inter-thread communication of data. They ensure propagation of values from producer to consumer without enforcing global order. On many architectures, acquire release correspond to very lightweight hardware fences or even no extra instructions, for example, x86. Okay, making them perform. The downside is that they require careful pairing logic, only synchronize on the same atomic variable and only when the load reads the value from the store. Okay, let's have some water, man. It's it's very, what do you call, time consuming. Hi, Italy, AU Italy, 10 million. Hi. Okay, memory order sequentially consistent. This is the strongest and default memory ordering sequentially consistent operation behave like acquire plus release combined plus an added guarantee of single order global. In which all the threads see all sequentially consistent operation in the same sequence. In other words, not only do sequence get store load act as full two-way barriers, no ordering around them in either direction, but all sequentially consistent operation across the entire program appear as if they occurred in a unified, consistent order visible to all threads. This makes reasoning about concurrency easier effectively. It is the closest to the simple mental model of one operation happens at a time in global sequence. Okay, this is a very, very good line, guys. This is a very, very good line. This is like very good information to gather for my understanding. Okay, let's go. What are you up to, AU Italy? The trade-off is performance. Sequence cards can incur heavier fencing on weaker architectures to maintain the single global order, which can become a bottleneck. Many high-level applications default to sequential consistent because it is safer and simpler to use. Uh, but in performance sensitive code, using acquired release or relaxed where appropriate can avoid unnecessary synchronization cost. Summary: relaxed gives no cross-thread ordering, fast but unsafe for communication. Acquired release gives one-way ordering. What is your monthly income? $1,000,000,000. That's my monthly income. Oh my god. Summary: relaxed gives no cross-thread ordering, fast but unsafe for communication. Acquired release gives one-way ordering and synchronization between two threads, just enough for the safe communication, more efficient than full fencing. Sequentially consistent gives strongest ordering, easiest to reason about. What is your month income? $100,000,000. Sequential control includes acquired release semantics as a subset plus additional global ordering controls. If you use only memory order sequential as an operation, you automatically get release acquire behavior where appropriate, but you also get a global synchronization that you might not always need. There are other memory orders. There are other memory orders like memory acquire release used for read, modify, write operations to apply both acquire release in one operation. Okay, memory order acquire release. Okay, and memory order consume, a weaker form of acquire, largely unused and deprecated due to difficulties in implementation. For this discussion, the key comparisons are okay. And why the heck did you say that? Common pitfalls and best practices with acquire release. Okay, using memory order acquire and release correctly is vital for writing safe, lock-free code. Here are some common pitfalls. Forgetting the pairing. Acquire and release only work as a pair. A store with release one thread must be ready to by a load with acquire on another thread on the same atomic variable to have an effect. Forgetting pairing. Let's try to see. I can paste it over here. Oh wait, why the heck I'm wasting time to paste. Let's go. Okay, using release on store but then reading the value with the relaxed load means you have no synchronization. Likewise, doing acquire load on variable that was never returned with the release give you no benefits. Always use them in tandem on the same atomic object to transfer information. Okay, assuming acquire waits for release. A very common misunderstanding is to think that acquire load behave not actually synchronized. Okay, let's just go with the summary now. um in summary, memory order acquire and memory order release from the foundation of lock-free synchronization. So acquires pull the other threads changes made before release so you can see them. Releases pushes out these threads changes so others can see them. They are cheaper than stronger ordering but demand careful pairing and reasoning. By following the best practices, always pairing release with acquire on the same atomic, or structuring code to respect the one way better, being cautious with the weaker ordering. You can use acquire release to build efficient, correct multi-threaded algorithm. Multi-threaded algo. And when in doubt, remember that the simplest correct solution, even if it's just using a lock or memory order sequentially consistent, is often better than a complex locks-free solution that is broken due to memory ordering bug. Okay, little bit of insights I got, you know. The goal is never to report a mean on any state that isn't the latest known correct state. So you get your get mean should probably return the mean of the queue at current last sequential state. If you have a gap, like you got sequential 5 and next you have sequential 7 with no snapshot filling 6 yet, you might decide that the state 5 is last known good state and anything beyond is unknown until resolved. Possibly get mean could return an empty invalid result if there is uncertainty, but the problem statement says we don't want to return a possibly invalid mean value. This implies that there is a gap in the sequence should maybe indicate no valid result. Perhaps return option double that is null until state is confirmed. Yippee! Hello, birds. Getmin should maybe indicate no result value, perhaps return an optional uh, double that is null until the state is confirmed. The interface even shows getMean returning optionable double, which supports this interpretation. The design tests how you handle out of order or asynchronous data, emphasize correctness, never let an inconsistent state through, and think about thread safety too. Likely this structure is updated from two threads, one reading snapshots, one reading incrementals. You may need locks or atomics to protect the state. In summary, if discussing this is something like maintain an internal queue state and last sequence apply updates in order. If a snapshot arrives with a newer sequence, trust it and reset state because it accounts for missed messages. This ensures our state is correct up to that sequence and only produce a mean when we know we have a continuous state with no gaps. This demonstrates understanding of the requirements. Oh my god, this is a very crazy task. Task dependency execution. The question about task with dependency is essentially asking how to schedule task given dependency graph. Use a topological sort. You can compute an ordering of tasks such that each task comes after all the dependencies, then execute in that order. If you have multiple threads on one machine, you could even run tasks in parallel. When their dependencies are satisfied, this becomes scheduling problem. Okay. um, a thread pool and dependency count per task can work. Initially, schedule task with no dependency, then as task complete, mark dependencies as resolved for others and schedule those whose all are prerequisite are done. Okay, cluster distributed. You'll need a coordinator. This is where leader election comes if no fixed coordinator. A straightforward approach. One node is elected leader. Using leader election algorithm or a state configuration, that leader knows the dependency graph and assigns tasks to worker nodes. It must handle if a node fails or so. Beyond scope here, but conceptually mention that in a cluster, network communication is involved, so task might need to ship input output between machines, and you might use a distributed network like how MapReduce or Spark schedule tasks using master node. You need to not cite those specifically, just the idea. Do you play NBA 2K24? Wait. This one? Okay, let's start again. You'll need a coordinator. This is where a leader election comes in. If no fixed coordinator, a straightforward approach. One node is elected leader. Using a leader election algorithm or static configuration, the leader knows the dependency graph and assign tasks to worker nodes. It must handle if node fails or so. Beyond scope here, but conceptually, he mentioned that in a cluster, network communication is involved. Tasks might need to ship input output between machines. You might need a distributed framework like how MapReduce or Spark schedule tasks using master node through you need to, okay, just the idea. As discussed, note the leader election ensures one node acts as a central scheduler so that two nodes don't try to do the same task or make conflicting decisions. If they press if the press mention an algorithm like Raft or Zookeeper, which many systems use for leader election, but likely acknowledging that we would designate or elect a single coordinator, avoid conflict is enough. Why use STD atomic? This was on your list and is straightforward. Okay. Safely share and modify data between threads without locks, and to control memory visibility and ordering. If they ask for specific, incrementing the counter for multiple or using int is not safe. Data race. Using std atomic int makes it safe and atomic. Also mentioned that the atomic operations can be faster than using mutex logs because they use low-level CPU instructions like atomic increment without context switching, but they are not a silver bullet, as contention on an atomic variable can still cause performance issue. Okay, very good. This is very good, very good, very, very good. Oh, wait, not here. Let's go, let's go. I tried something different this time. Okay. Binary tree. Okay, as contention or atomic variable can still go on cache code and traffic. Binary, not explicitly, but sometimes comes up. If you recall basic tree travel, simple, it can't hurt to revisit. JSON merge. Merging two JSON objects likely means writing function to take two data structures, perhaps two nested maps, or parse and combine them. The rule might be that keys present in both, you merge their values. If values are themselves objects, recursively merge. If they are primitive arrays or perhaps one override, or you combine into list depending on spec. Since specifics aren't given, just be aware how you would approach merging hierarchical data. If you have time, server monitoring system design. This sounds like a system design plus coding hybrid. You receive periodic files from each server containing timestamp temperature readings. Clients will query this data from a time range. You need to design how to store the data, answer queries efficiently, possibly across many servers' data, since each server sends a file, maybe daily or hourly with the timestamps temperature. You could append this data to a central database or keep a separate logs per server. A simple approach store each server's reading in stored structure by time, even just an array or vector, since appends are in time order presumably. For querying, if it's per server query, you binary search the timestamps to get the range. If across servers, you might need to merge results from multiple sorted lists, similar to merging k-sorted lists. They also mention serialization, deserialization. Perhaps the files are in some format. You need to pass them into memory and maybe write them out later in a compact form. Given time, focus on algorithmic optimization. Presumably, they want to see you handle a lot of data efficiently. Hi mate, hi Sai, how are you? Maybe use memory map files or stream processing to avoid too much memory overhead or compress data in memory. For coding, if a simpler version is asked, given multiple sorted logs of time value, implement a query that returns all the values in time range. Then you'd likely merge results with two pointers technique or binary search into each log's range. Fine, just wrote TCS exam yesterday. How was it? What do you think? Will you get the TCS job? Then you'd likely to merge results with two pointers. Compiler sucks. I know how to solve it, but what do you mean compiler sucks? You mean online compiler? Also think about the edge cases. The compiler they provided in the exam. Exactly, okay, online compiler. What, why? No data, also think about that, no data available, or the range has no readings, or overlapping time, etc. The, this question is open-ended, so if it clarify requirements, talk through the design. Okay. Random element from one order, so this was explicitly described. Essentially implement a data structure like std order set, but with an added method sample that returns uniformly random element. This is exactly like insert delete get random problem. The known solution is to use an array vector to store elements plus a hash map to map each element to its index in the array. For insert, add element to vector, record its an index in the map. To remove its index from the map, swap the element to the last element in the vector to get Update the moved elements index and the map the pop last element. Okay, I see what you mean. Get random is just pick a random index and return the element at the index in the array. This yields average of order of 1 for all operations. Okay, if you recall this approach, you can implement it quickly. Just be careful with the details. Updating the map after swap, handling when the set is empty. Forget, you can reason it out. The main challenge is how to remove order of 1 while still being able to get random or swap trick is the key. Also mention that random can be used for the random part, but they won't focus on the randomness method as much as the data structure. Compress array of numbers, delta encoding problem. This was a bit complex sounding. Compress list of numbers by sending deltas that fit in 8 bits, and any number that doesn't fit that scheme send via different mechanism. Essentially, you want to maximize how many numbers can be represented as an 8-bit delta from the previous number. This solution hint given. Hi, Dr. Reviews. Hi, what's up? I love your streams. Thank you so much. Okay, compress array of numbers. This was a bit complex sounding. Compress list of numbers by sending deltas that fit 8 bits. Any number that doesn't fit the scheme send by different mechanism. Essentially, you want to maximize how many numbers can be represented as an 8-bit data delta from the previous number. The solution hint given. Sorted list. They use sliding window to choose the largest subset where consecutive numbers differences less than 25. 255 fit in 8 bits. If this comes up, outline that you'd sort the data, then find the longest subsequence or the window where each adjacent difference is less than or equal to 25. Those can then be compressed. Send first number fully, then deltas for the rest. Numbers outside the window or the break the chain would be sent separately, perhaps individually. This problem does greedy rendering approach and understanding of data compression. Oh wait. 5. What is 5? Okay, I will continue that part later. Let's focus on this. Atomic library introduced. I don't know. Randomly you are saying things, yeah? Introduce atomic types, manage concurrent access to shared data without data races. Atomic is template that wraps the type T into atomic object. The key properties, the read and writes on the atomic object from different threads do not cause undefined behavior. Unlike normal variables, in other words, if one thread writes to an atomic variable and while other thread reads it, the behavior is well defined and free of data races. Okay, this is a very good way to learn. Will you be streaming tonight? I'll try. I'll try. Okay, let's go back and read. Oh my God, look at my eyes. Oh my God. It's fine if you don't. I will just watch your streams tomorrow. Thank you. I will definitely stream tomorrow. Yo, what's up? What's up? You tell me, what's up? How are things? How are things? You're gonna be good streamer one day. Thank you so much. I don't know when. I'm trying my best. I am literally trying my everything, all my energy during the weekend is going on streams. Okay, let's continue reading. So, introduce atomic types to manage concurrent access to shared data without data races. Is tablet that wraps type T? Suggest a song, bro. For what? For what? You need song for what? To listen. Oh, to listen. Have you tried EDM? Electronic dance music? You can listen to EDM songs. You will have 1 million subscribers one day. Thank you so much. It means a lot. You're wishing that thing for me. Currently, I just have 1400. I do think same, bro. Have something. You will hit 1 million. I just subscribed. Thank you so much. It really means a lot to me. What are you guys doing on Saturday evening? Or whatever the time is there. It's a beautiful day. Trust me, it's a beautiful day. Rainy, shiny, beautiful day. I don't know. Same here. I'm just reading things on beautiful evening. I'm just reading, you know. It's 12:09 over here in the night. Where are you from? It's raining for me. It was raining here, but it's not raining anymore. From the Philippines. Oh, in Philippines it's 12. 9:39 back in India. It's 17 degrees. Wow. Oh, I don't know what's the weather like here. Let me check. Yeah, here 17 degrees. Correct. But it feels like 7. It feels like very, very cold. It's 5:10 for me. Exactly. Same here. 5:10 for me as well. UK guys. The key properties that reads and writes on atomic object from different threads do not cause undefined behavior, unlike normal. In other words, if one thread writes to an atomic variable while another thread reads it, behavior is well defined, free of data races. This allows threads to communicate or update shared values safely without using explicit locks, enabling lock-free programming when appropriate. Atomic operations are often implemented using special CPU instructions like compare and swap, so they can be much more efficient than using mutex locks in low contention scenarios. Also come with complex memory model and ensure correctness. Okay. Let's try to grab some info here. Okay. And let's go this way. Perfect. I'm now gonna sleep. See you later. Thank you so much for joining. Good night. Have a good one. Sleep nicely. And I will see you tomorrow. Purpose. The primary purpose of S3 Atomic is to provide thread safety. Atomic read, modify, write operation on a shared variable. This helps prevent race conditions where threads might otherwise intervene operations on ordinary variables. By using standard atomic, developers can build synchronization primitives or simple log-free data structures like counters, flags, without resorting to heavier mechanism like mutex. Additionally, atomic operations. I'm back. Welcome back. Additionally, atomic operations can enforce specific memory ordering constraints like below to synchronize memory across threads. Note that S3 atomic objects are neither copyable or